Okay, I think we can start. Well, first of all, thanks for joining this new ChEESE webinar. Today we have the pleasure to have Marta García-Gasulla with us. As you know, she's also in ChEESE, part of task 2.4 on performance monitoring. And today she will talk us about this tool, the Tracking Application Live Performance, TALP, which is a part of the DBL library, if I'm not wrong. So this is a tool that, as you know, we plan to implement in several of the flagship codes within this task 2.4. So it's very timely because this task has started now in the second half of the project. So it's time now to learn more about TALP, the new developments, which is the status, and how we could or should integrate this utility in some of our flagship codes. Just to remind you that we are recording this webinar, so if anyone is against, step in now. Otherwise, we will record it and post it in our YouTube channel and other social media. Okay. So Marta, thanks for being here, and the floor is yours. Marta, she told me that it's going to be quite a short, 25 minutes maybe, or half an hour maximum talk. So unless you don't have a very, very urgent question, we prefer to have all the questions at the end. You can post them on the chat nonetheless, and then we will take all the questions at the end of Marta's presentation. Okay. So thank you.
Thank you, Arnau. Yeah, as Arnau was saying, just take note of all your questions and we can discuss at the end. So I'm going to present the current status of TALP, but let me put you in context, because sometimes you will see that we say that you need to have this DLB version or that other. So TALP is part of the DLB library, and the DLB library has 3 different modules. Although today here I'm going to talk only about TALP. We have LEWI for dynamic load balancing, DROM for assigning resources, and TALP is the one monitoring. They share the API, and they share also the shared memory and the data that is stored. But they can work completely independent, and coordinated. So you can enable more than one module and it will still work. But today the presentation is only about TALP. And what is TALP? Well, TALP is a profiling tool that the idea was to design it with a very low overhead so that you can use it with your simulations, with your production runs, to get an understanding at the end of the execution of how efficient your execution was. We report POP metrics. I will explain later on what are the POP metrics, and we will see that there are different kind of metrics, let's say. And it provides also an API to obtain these metrics at runtime, and another API to instrument your code, because you say, okay, I don't want it to be so transparent. I prefer to have regions because I know very well my code and I want to get the metrics separated. We offer an API for that too. The current version is 3.5.1. And this version includes the MPI efficiency metrics, which are very stable. They have been implemented for quite a long time. You can see here the first paper that we did with TALP. And it collects also hard-won counters. So this way we can provide information on the number of instructions, the IPC, and the frequency at which your code was running. We have also implemented OpenMP efficiency metrics. And we also have what we call TALP pages, that it's a facility to integrate TALP within a CI/CD infrastructure. And the work in progress is adding GPU metrics to TALP. I will present in detail all this, and I will give you a first preview of the GPU metrics because everybody is very excited about this. But first of all, let me clarify what are the TALP MPI metrics and the POP metrics, and which is all this concept of efficiency metrics. So these efficiency metrics that we talk about come from the POP project. And the idea is to report metrics that are based on how efficient the code is using the computational resources. These metrics are organized in a tree. They are hierarchical. And they are multiplicative. So every parent is the product of their children. The basic set of metrics is this one. It's a very well-defined and very established one because it has been running since the first pop-up project. And the idea is that the ones that are on green are efficiency metrics and are compute how well the computational resources are being used. So how much time you are losing due to the parallelization, let's say. The blue ones are scalability metrics. These ones only take into account the compute time, so the time that your application is doing useful work. And in this case, they are scalability metrics because they need a base case to be computed, because we don't know if the number of instructions needed to run your code is enough or too much, or so we need a base case. That's why these blue ones, they need a base case, and you can compute then based on that. So which is the difference between these, which are the original POP metrics and the TALP metrics that we provide? The first difference is that we cannot divide this communication efficiency between serialization and transfer, because to divide these two metrics, we need a simulation that we do using an external tool, and you need a trace for this. As we are only gathering metrics and we are not gathering traces, we cannot divide between these two. We stay here in the communication efficiency. But we add two new metrics, which are the load balance. So this is load balance in, and load balance out. These metrics, the idea is to give you the measure of how much of the load balance is happening inside the nodes or outside the nodes. So this is the global load balance between MPI processes. And with this division, we understand if the load balance is happening inside or outside the node. At this point, usually some users ask me, why do I need another profiling tool? Or I already have my own profiling mechanism inside my code. So the advantage of using TALP is that we get these efficiency metrics that give you more insight on what's going on in your simulation. It's not just numbers, how much time you're spending inside MPI, but really giving you information on why that time is being lost. So to understand this, we have two applications, application A and application B, with two MPI processes running in two CPUs. Here in application A, we see that there's a load imbalance. So the first MPI process finishes the work faster, while the second one takes longer, and the first one needs to wait for the second one. In the application B, we have two processes, each one running in two CPUs, and they are doing a lot of point-to-point communication between them. So if we add the amount of MPI time spent in each one of these applications, we get the same number. So this is what a regular profiler will tell you. You are spending this much time in an MPI. The nice thing is that TALP will tell you that application A has a low load imbalance and application B has a low communication efficiency. And you will see that in this case, maybe you need to do a different distribution of your work, or your mesh partition is not efficient. And in this case, maybe the problem is too small and you are spending too much time communicating that data compared to with the amount of work that you have. So that's why we say that TALP gives you more insight with these metrics on what's going on than just a profiler that measures your time. A bit more on how we compute the TALP metrics. So this is what a drawing of an execution where blue is computing and red means waiting in MPI. In this case, the parallel efficiency is how much time do I spend in red, in MPI, compared to the whole time that I'm using the resources. This is the parallel efficiency, how much time I'm using efficiently the resources to do useful work. To compute the load balance, what we say, okay, which is the most loaded process and how much time I'm wasting because everybody else is waiting for this more loaded process. So it's all the yellow part here. So this is the most loaded process, and then all the other three processes are waiting for them. So load balance would be the yellow. Here you have the formulas, and here you have the example. If we take these numbers, which are the values that we will get. Lately, the communication efficiency is the orange part, is the time that it's lost because of the most loaded process is waiting in MPI. So the idea here is the load balance tells you the efficiency that it's being lost because you have one process that is working more than the others. And the communication efficiency tells you the time that is being lost because you are waiting in MPI, but not due to the waiting for the most loaded process. This communication can be then divided between serialization and transfer, but with TALP we cannot do that. So what about the load balance in and load balance out? So for the load balance in, what we do is we compute the load balance inside each node. So just taking into account each node separately, and you get the load balance for each one of the nodes. And then the load balance out is the time that you spend, the time that you lose because one node has more time, more load than other. So what we do is we add all the compute time of each node and we compare them. So the node 1 is more loaded, and because of that, node 2 is waiting for it. So then, based on this, the load balance in is the load balance in of the node that was more loaded. So that way we know that if we are able to load balance perfectly inside each node, that's what we will gain using what we will gain with load balance in. And if we are able to balance between nodes, that's what we will get with the load balance out. This is useful for us because one of the things that we do inside the DLB library is load balance inside the nodes. So these metrics tell us if it's worth enabling DLB, dynamic load balancing, in our simulation or not. That's why we added these metrics. So now I explained a bit the most basic metrics of TALP, and now I'm gonna talk about some different use cases, because sometimes I say that TALP is transparent and can be used without doing any change on the code, and then I also say that we have an API. And so I present this as 4 different use cases to give you an idea of the kind of things that TALP allows you to do. So I will present this, the completely transparent use for the user, to add defined user regions, to get metrics at runtime, and the TALP pages to do continuous performance monitoring. So the most basic use of TALP is this one. You just need to export this environment variable where we tell the DLB library that we want to enable TALP and that we want to get the POP metrics. Then we LD preload the DLB library with MPI interception, and then we run our application. Just adding these 2 lines in your script will get you, at the end of your execution, a summary like this in the standard output. We print it in the standard output, but we also print it in a text file, in a JSON file, in different formats so that it's easy. So this is more user-friendly. The others are for processing with other tools afterwards, if you want. But the idea is that you will get the different metrics with the hierarchy that I was explaining before. Regarding the computational scalability metrics, as we cannot compute the scalability metrics because we have just one run, what we report is the value, so that the user then, gathering this information from different runs with TALP, can himself compute the scalability metric for this value. So you have the useful IPC, the frequency, and the useful number of instructions executed. The way this works is that you have your regular application, that it's working with MPI, running in several cores, and when an MPI call is executed, using PMPI, which is a standard feature of MPI libraries. We intercept the MPI call, and through TALP, we record the time that is being used for MPR or for compute time. So every time I enter and exit an MPI call, I record here how much time I spent inside the MPI call or doing computation. With this, at the end, with some formulas, I am able to provide the metrics. You can also get the raw data, which will be the data that we collect here. But for the regular user, what is interesting is this to obtain the information on how your execution was. This is the most basic case. Then if you want to do something else, you say, okay, I know my code. Now I see that TALP is very useful. I get my first metrics. And now I'm excited because I want to understand if my imbalance is inside the solver or it's inside the initialization or whatever. So then we provide this API where you define what we call a monitor and you give it a name. And then after defining that monitor, you can start and stop whenever you want that monitor getting data. This way, at the end, what you will get is the same metrics, but divided by region. So you always have the main one, which is your whole execution. This is the same that you get with the transparent, completely transparent use case where you don't do anything. You get the main one, so taking into account all the execution, and then for each region that you defined, you have the name and the metrics. In this case, for example, the kernel computation region didn't have any kind of MPI code. That's why it's not showing the MPI efficiencies. So it's just showing the computational metrics. In the main loop region, we have this region includes MPI code, so then we see different values for the parallel efficiency of the code, and you still have also the computational metrics. So the regions can be nested as you want. There's no requirement, so you just need to, each one of them needs to be make sense standalone. Let's say you need to start and stop them, but you can have nested regions, smaller regions inside the bigger ones, or then one starts or another starts and then ends the second one and then ends the first one. So you can nest them as you want. There's no limitation in this sense. Okay, you want to do one step more. In this case, we can get also the metrics at runtime. So you can, in your code, use another API where, based on a region, you can get the region here. Based on a region, you get the different metrics. This works the same way. So we intercept the MPI calls, we store all the data, but then we offer this API that can, through TALP, can gather the raw data or the metrics. The nice thing of this is that at this point, then you can take decisions. So you don't need the simulation to finish. Imagine that you're running a simulation and you're getting very bad efficiency metrics, and you detect that in the fifth time step. Then you decide to kill that simulation and start over again, fixing the load imbalance, for example. So this allows you to take decisions at runtime. They could be as simple as that. So if I have an efficiency below a number, I just kill my simulation. Or they can be more elaborate. They can be used also by external entities like resource managers, dynamic resource managers, or things like that. So to understand a bit better this, here I have an example that we did with a code where Alia, that it's the code, was requesting the efficiency to TALP. So it was gathering the efficiency metrics from TALP. And based on those efficiency metrics, it would decide to increase or decrease the number of resources where it was running. And then using comps, it will really increase the number of resources of the simulation. So for this, we set a target efficiency. Okay, and in this case, it's the red band here, for example. The blue line is the number of cores that the application is using, and the red line is the communication efficiency, which was the target. So what we wanted to have is the communication efficiency between 0.98 and 0.97. So the communication efficiency started here, and at some point we said, okay, the communication efficiency is too low, so let's release some resources to see if we get to the target communication efficiency. So we released these resources. Now we are running with 40-something cores instead of 90-something. And we see that the communication efficiency improves, but we are still not in the target zone. So we keep decreasing the amount of resources. And now when decreasing the amount of resources is when we get to the target communication efficiency. We had the opposite example where this is the target communication efficiency and our simulation was above. So in this case, we keep asking for more cores until the communication efficiency was in the target zone. This is an example of something that was more complicated, trying to reach that communication efficiency without stopping the simulation, just doing it dynamically. And the fourth use case that I was talking about is the TALP pages. The TALP pages is used for doing continuous performance monitoring. And the idea is that you do some development in your code. You do a commit to your GitLab, whatever. You usually run your correctness test in your code. And after running the correctness test and passing the correctness test, then we run some performance test using TALP. TALP will give back the metrics. And based on these metrics, we can plan the new developments based on the data that we have seen. And then we can start again. So the idea of this is that you can integrate it in a CI/CD platform to detect the performance issues added to your code with a commit every sometime. We have basically present two visualization modes. One is the scaling efficiencies, where for a single commit, you get different the metrics for different configurations to understand better where you are losing the performance. And the metrics evolution, where you get the metrics for different commits and you plot it like a timeline, and you can see the evolution of the different metrics with the different commits. So what do you need to do to get this running? Inside, we don't provide the infrastructure to do this. So you should have your own running instance of GitLab where you have all your code and you run all your tests. And then when you say, okay, when I do a commit or a merge, or you decide when you want to schedule this, you will run some runs that are for getting the metrics. In this case, we want to do scaling runs, so we get 3 different executions, and we gather the data from TALP in a JSON file. With this, we are able to build some HTML pages that will show in the GitLab pages. So this is an example of something that you could get. This is the scaling efficiency. So for a single commit, you have different configurations. In this case, it is a hybrid MPI OpenMP application, and you can see how changing the number of processes and threads, you get different metrics. The other version where you see the metrics evolution is something like this. So here in the x-axis, you have the different commits. Every point is a commit or a merge. And you see how the different metrics evolve. In this case, this is time, this is IPC, number of instructions, and efficiency. And then you can also select the different regions. If you have identified regions inside your code, you can also check these metrics per region. So this gives you an idea. In this example, there was an optimization done to solve a problem that was detected. And then we see here how from this execution here to this one, the parallel efficiency in these two regions was improved. Okay, now I started talking about the MPI metrics inside TALP. I'm going to give a brief overview on the OpenMP metrics. These are also implemented in TALP, but they are not so stable as the MPI ones. We are not because they don't work, but because we are still deciding how we compute some of the metrics. So these are the metrics that I was presenting before. What we do now is we keep the computation scalability metrics the same way, but now we add another branch here, which are the OpenMP parallel efficiency, and we have a global parallel efficiency. So the global parallel efficiency is how much time you are doing useful work and not time being lost due to MPI on OpenMP. And then for each one of the branches, the MPI parallel efficiency works the same way as I explained it before. And the OpenMP parallel efficiency, we divide it in 3 different factors. Load balance, so time lost because one thread has more work than another one. Scheduling efficiency, which is due to work that I need to do in the OpenMP runtime. So I need to do the reduction, I'm creating the loop, I'm creating task, this kind of more like overhead. And then the serialization efficiency, which is the time that it's lost because not all the code is parallel inside OpenMP. So this accounts for the regions that are serial and are not inside an OpenMP parallel. And this is an example of that you will get, the report that you will get when getting the OpenMP metrics with MPI metrics. So you get both the global parallel efficiency, then divided by MPI and OpenMP, with the child metrics inside, and also the computational metrics. To use the OpenMP metrics, you need to do the same thing as with the MPI metrics, so LD preload the library. The only thing is that we need OMPT to intercept OpenMP, so you need to use an OpenMP runtime that implements the OMPT part. The OMPT is a standard interface in the OpenMP that is for tools attaching to get information. And I will finish with the GPU metrics that, as I said, this is work in progress. This is not done yet. We have a very first implementation of a partly implementation. But I want to present a bit the idea that we have on this. So the idea for the GPU metrics is to split completely the efficiency of what we call the general purpose or CPU and the accelerator or GPU. And the idea is to not provide, and so we don't have any kind of product here, because then means that you need to give a weight to each one of them. Do you account the same for the node, the CPU node, that for the GPU, or this is 10 times more important? So I don't give a weight, so I get 2 separate set of metrics that they are not computed together for anything. Then the general purpose metrics are basically the same thing that I was presenting before. So we have the parallel efficiency and the computation scalability. Here I don't draw the other metrics, but they are still the child metrics, but they are still here. So inside the computation scalability, you have the IPC, the instructions and the frequency. So everything is the same, with the difference that I add a third child to the parallel efficiency. So before I had the MPI parallel efficiency and the OpenMP parallel efficiency, and now I have the accelerator parallel efficiency. What is this? This is the time that I'm losing or not using the CPU or the general purpose due to the fact that I'm using an accelerator. This means that the time that I'm launching kernels, or the time that I'm waiting for kernels, or the time that I'm moving data to the GPU, this is all time that it's accounted in this efficiency. Now, for the accelerator, we have the same structure. We have the accelerator, we have the global efficiency, and we have two childs, the accelerator parallel efficiency and the accelerator computation scalability. These two childs also will have their own childs, so as in the general purpose. But I don't present it today here because we have not finalized how they will look like yet. But the idea is that there will be several childs in each one of these metrics. The idea is the same one as for the general purpose. The parallel efficiency of the accelerator will tell us how much time I'm using that accelerator, and the computational scalability will tell me the time that I'm using it, how well the resources are being used, how many streams I have running, how many instructions I'm doing. This is something that we will compute in the child metrics of this metric. So this is a very first draft. As I said, the current status is that we are able to get the metric, the accelerator parallel efficiency. So you can see here an example where we have the parallel efficiency, the MPI parallel efficiency, and then as is a CUDA MPI plus CUDA application, I see also here the CUDA runtime parallel efficiency that will be this pink box here. Then when this is done, we will also see the NVIDIA device. So we see now that we have two devices, the host and the NVIDIA device. And then the NVIDIA device has its own parallel efficiency that it's, well, now shows some zeros because we are not computing it yet. So as a summary, what we have implemented and testing in a very early stage is the general purpose accelerator parallel efficiency for NVIDIA and AMD accelerators. The work in progress is the parallel efficiency of the accelerator device for both the NVIDIA and the AMD accelerators. So as a summary, DLB is in version 3.5. The MPI metrics are fully supported, are completely stable. The OpenMP metrics are under testing. They are stable, but we are still developing some things in that part, but they can be tested. And the GPU metrics are in a very early stage of the development, where we can get the general purpose metrics, and this is under testing, and the accelerated part of the metrics that are under development. You have here some useful links. You can download DLB. You have the user guide where you have all the definition of all the APIs that you can use. And we have also some hands-on if you want to play with it, with some toy applications or super simple benchmarks to test the different functionalities of the DLB library, and it includes a TALP hands-on. So the idea that I wanted to share to you, and that I wish is what I get, is that TALP is a lightweight tool that allows you to gather efficiency metrics. We can gather these metrics at finalization, which allows you to to understand how your simulation was using the computational resources you are running on, and also to implement continuous performance monitoring with the integration also with CI/CD systems. It also allows to get these metrics at runtime, and this allows the application to take decisions at runtime. So if you decide to kill your application or change the amount of resources you are using. Its low overhead allows its use in production runs. So we have measured its overhead, and we have improved it a lot since since the beginning. The nice thing is that it does not store terabytes of data, so we gather aggregated metrics, and it provides an API to annotate regions so that you can also maximize the information that you get. And the idea is that this is not a performance analysis. This is just a tool that will tell you when you need a detailed performance analysis. So we get some metrics, but sometimes this is not enough. So you need to end up getting a trace and doing an analysis. But with TALP, we will know when exactly you need that analysis and in which use case. So if you have several runs and you see that one of them is the one that is dropping the efficiency, you know that that's the one that you need to analyze. And that's the end of my presentation. Thank you very much, and I will be happy to answer any question or anything that was not clear.
Okay, thank you very much, Marta. Very enlightening and clear presentation. So thank you very much. So we open now the floor for questions. I see one in the chat, but raise your hands or just step in. There is one from Christoph Nehammer. He's asking if TALP is used in a CI/CD, for example, GitHub, where runners are Docker containers or virtual machines and may run on different hardware with different performance. What recommendation for using TALP in this environment can you give?
That's a good question, and it's adding layers of complexity to the thing. I think you can use it the same way as we suggest to use it regularly for anybody. But you need to take into account that, for example, the computational scalability metrics or the IPCs or the frequencies, as you may end up running in different hardware, may vary. So if you really want to understand if the change in your code, there was a change in a metric related to computational scalability, for example, IPC. So you are trying to solve an issue with IPC, trying to improve data locality, then I would suggest to do that run in the same hardware. If not, for the parallel efficiency metrics, you should rely on what TALP gets you.
Okay. More questions? Yes, there is a, I think that Victor is providing an explanation, no? Yes.
Yes, we have a small example.
Yes, I see Piero.
Hi, Marta.
Hi,
Sorry
Piero.
for the camera. Yeah, we discussed it also during the work packet for ChEESE. The alignment of TALP metrics with POP metrics. So at a certain point, they will recombine, also taking into account the differences, of course, that you already explained, or they will continue in a separate branch.
That's also a good question. And that's one of the reasons why I keep saying that OpenMP metrics are under testing. So basically, the MPI metrics are the same ones. For the OpenMP metrics, I hope that when we have, so the idea, well, both for the OpenMP parallel efficiency and the GPU ones, when we have really defined the metrics that we want, and we can present some examples showing the benefit of computing the metrics this way, my plan is to present it to the POP project, and there's hope that they will be taken as the official ones. But I cannot tell you right now that it will be so. So I need to convince them. the idea is to get enough examples and and to be able to show the benefits of these metrics of using these ones or not, and not other ones. It's quite similar. One of the differences, for example, is that in some of the metrics that we compute, we don't keep the fact that they are multiplicative. One of the reasons is that when you have a hybrid parallel programming model, the time that is being lost is not so clear that can be assigned to one of two of the programming models. And the current version of the POP metrics assign that to just one of the parallel programming. So let me explain this with an example. If you have an MPI process that is doing a lot of communication, the time of the threads that are blocked while the main process is doing communication is due to MPI or OpenMP. Well, you can compute it one way or the other, but what I say is that it can be blamed to both programming models, because you can solve that issue either doing less computation, and then the threads will be less time being underused, or you can improve that by overlapping computation and communication.
Yeah, sure.
Exactly. And then you solve it using OpenMP, because if you are able to overlap tasks. So that's why I defend that maybe we don't need to keep them always multiplicative, and that then just compute what you can improve, which is each one of the different parallel programming models. But yeah, I'm talking a lot. Sorry. It's the short answer is I will try them too.
Yeah, sure. Thanks.
But I cannot ensure that now.
Very interesting.
I see no more. If not, I have maybe one about instrumentation, no? Because if I understand, if I do nothing, I just analyze the whole application, no? But then I can instrument either for runtime or for narrowing down the focus of analysis, let's say defining my own regions. That's clear. Now, how I do that? I do that by inserting some pragmas. Apparently here it's exactly. So
No,
is this for a C-like syntax, or just I can also do it on Fortran, for example?
No. You can. We have interfaces for C and Fortran, but they are not pragmas. So this means that you really need to link, compile, and link with DLB. So you need to include. So the main difference is that you don't do anything to your code, and you don't need to recompile, and you get the metrics for your whole run. And if you want the regions and more detail inside the code, then you add this dependency with DLB, where you need to include
that
it.
was clear. That was clear. Now for GPUs, am I limited to CUDA, or for example, you plan to have OpenACC or others? Let's say I have a code with OpenACC and I want to instrument it. Would that be possible? Will that be possible or not?
But at the end, so if I'm running in an NVIDIA GP device, OpenACC relies on CUDA below. So we intercept the kubT and inside, well, not kubT, the kubT stuff. So I think as far as it's an NVIDIA device, so that's why I was mentioning NVIDIA devices and AMD devices, because we are trying to intercept at a low level so that you have a programming model on top of that. We will still get that. I don't know if you want to add something, Victor, or if it was correct what I said. But...
Yeah, I think that's correct.
Okay. So then if you have already tested on AMD, it means that you have also deployed these on Lumi or in other machine different from Mare Nostrum 5, right?
Yes. Yeah. So TALP is available in Mare Nostrum 5, for of course, in the accelerated and the general purpose partitions, but we have also it in Leonardo and Lumi.
Perfect.
And we are targeting to get it also in the other Euro HPC machines.
Great. Anyone else with questions, comments, suggestions? So now I'm wearing the ChEESE hat. If we have to implement this in some of the codes, would you recommend to wait a bit more, or what are your plans for having the GPU version? I don't want to say, let's say, finished, but more or less reliable.
My wish is to have it before summer, so something that at least we can test. So yeah. Meanwhile, if you say, okay, I would like to give it a try to understand how easy it or how difficult it is, you can still use the current version and get the MPI metrics so that you can get that idea of, okay, this really is easy to use, really doesn't add overhead. So getting this first idea, you can already do it. And the plan is, to have something during the following 2 months, a first version running.
Okay, there is a question from Iskander in the chat. How do I find it on Lumi, module load DLB or module load TALP? Victor is replying already.
Yes, we have it locally so we have it installed. We know that it runs, but we were requesting the user support to add it as public modules, but it's taking time for them to answer us.
Okay.
For the OpenMP target of load, I guess it's the same answer. So I guess that it will run through kubectl at the end. So if it's an NVIDIA device, you will get the same information. But we will be sure to test it when we have it finished to see.
Okay. There's no more questions. So we are in perfect time. Remember that we will record this, so you will have the opportunity to go back again to the presentation and look it carefully. Thank you very much, Marta and Victor, behind the scenes, replying questions. And that's it. Hope to see you in the next webinar. We don't have it, the next one is scheduled, but you will have news very soon. We were talking with Ayrton before, so we plan to have the 4th or the 5th, I don't remember well now, webinar before the summer. Thanks for attending, and especially thanks to Marta and Victor. Okay.
Thank you for the invitation.
Thank
Bye.
you. Pleasure. Bye-bye.
Bye-bye.
Thank you very much.